Okay, good morning everyone. We are going to talk about electricity generation. Like how do we generate electricity in this case? So have a look at this video. Okay, so it starts with a DC motor. Then as it goes, so what happens is as it turns, instead of connecting electricity to it, as we turn the shaft, there is going to be um, electricity produced. Okay. So now when we connect one DC motor with another DC motor, say what's going to happen. Basically, as this guy turns the shaft, electricity is produced, and the induced electricity, the induced current goes to the other DC motor, then it turns. So again, similar concept applies. If they, yep, just have a look. Um, this thing there is nothing more than a piece of magnet and a shaft with some wires inside. So he turns one, and automatically electricity is produced. So, yep, this is just a classic example of a DC generator. So DC motor and DC generator. But in production, what's happened today in the power plant, we don't use DC generators. We use AC generators, but we don't call AC generators AC generators. We call them AC alternators. So if you look, here is a diagram of the design of an AC alternator. Look, this is the top view. We have It's very similar to DC motor but different because there's no commutators. We don't use commutators. Now, if you look at the top view, we have a we have a magnetic field. Okay, go to the right, and we have basically uh, a square. Well, we have a wire that rotates in a square, something like that. Okay, and the central shaft is here. Okay, so basically what's happening is if you rotate this thing, it will produce electricity. Okay? And, and let me draw some side views so we are able to, I'm able to explain what's happening there. Okay, so here are the side views. As the shaft rotates clockwise, okay, yep, you see the side view, how does the side AD, basically how does this coil okay, rotates. Okay, it looks like this. Now, open your cheat sheet, go to your cheat sheet, and have a look at Faraday's and Lenz's law. Okay, so yep, here, actually the induced current law here. So I will write it down. Okay. Faraday and Lenses told me okay, the induced EMF Yep, is basically minus n is the number of coil of times the changes in magnetic flux over time. Now have a look what's happened. Well, let me write down the formulas for the magnetic flux. Magnetic flux is calculated with the magnetic field times the area. The magnetic field times the area that the coil has, as the coil is circulating. So look at position 1. When that coil is flat, when it's flat, tell me what is the value of magnetic field? Sorry, what's the value of magnetic flux? Without doing any calculation, I can tell you the magnetic flux, the value of magnetic flux will be 0. It will be 0 because when it's flat, the area lies parallel to the direction of magnetic field. There's no area that interacts with the magnetic field. The flux is 0. As we turn it 90 degrees over, the value of magnetic field is maximum. Because at this point, we have maximum area at position 2. We have maximum area under the influence of magnetic field. They are perpendicular. When it's flat, there's no area on the perpendicular direction. They're all in the parallel direction. When it's perpendicular, it's maximum. Then again, at position 3, it rotates 180 degrees. The area is flat. The magnetic flux is 0. Position 4, 360 degrees. Yep. Now I think, yep, okay. No, sorry, 270 degrees. Yep. Yep. The magnetic flux is maximum. Okay. So what's happened is we observed the change in magnetic flux as we rotating the coil in a magnetic field. Since there's a change in magnetic flux over time, current can be produced. And since if the rotation is constant speed, we can produce we can produce it going to the AC current. Now, just let's do some activities. Let's find the direction of the current. Initially, at position 1, I have force acting upwards because basically someone or something is going to rotate the shaft anti-clockwise. Okay, so at point A, I have current going upwards and the magnetic field lies to the right. Use your right hand rule and remember Lenz's rule. Okay. At your right hand rule, just remember Lenz's rule. Okay. Lenz's law told me the induced current will be in the direction so that it will oppose the change. Okay, it means the induced current will be in the opposite direction. Okay. So if you try to do it, yep. So let me do it. Okay, let me do it. So force is acting up, and what's happening is the current tries to pull it down. Remember Linz's law from last week? We apply a force upwards, but the wire is not happy. The wire wants to stay there, so it pull me down. The wire generates a force downwards. So what you do is you put your palm down and put your finger from to the right. Okay? Then you have your thumb pointing into the page. Okay? So the induced current have a direction into the page. Okay? That's the induced current. And in contrast, okay, so the current come out of page at this point, at position A, okay, as we rotate it. And then, yep, okay, and then at this point, okay, well, the current still goes in and comes out. Okay. However, at this point, the current actually is 0, but I still, okay, let me leave. Okay. Sorry about that. Let's go to position 3. If we do position 3, okay, remember it's always rotating clockwise. We do the same thing. Okay. So we have a force acting upwards at point B, but the wire wants to go downwards. Okay. Linz's law. Then we have magnetic field, so use your right hand rule, induced current goes in and comes out on the other side. Okay. That's the direction of induced current. Yep. So, yep. Now, if someone asks me to sketch a graph of the current, well, let's sketch a graph of magnetic field first. A magnetic flux. So if I'm going to sketch, let's forget about current for now. Let's just concentrating on magnetic flux. If I'm going to sketch magnetic flux, initially the magnetic flux is 0. After a quarter period, after it turns 90 degrees, the magnetic flux goes to maximum. Now, after it turns 180 degrees, the magnetic flux is 0. Then, afterwards, the magnetic flux is maximum again. But in this time, you say how does it rotate? As the direction changes, it goes like this. Then it rotates back. So if I sketch the magnetic flux over time graph, I get a perfect sine graph. If the shaft rotates at constant circular speed, we have a sine graph. So from Faraday and Linz's law, okay, the voltage or the current over time should be the gradient, okay, of it. Yep. So what's happened is initially the current, if you look at here, initially the magnetic flux is 0. However, the rate of change of magnetic flux over time is maximum. Okay? So what we do is, I will have a maximum voltage because the rate of change of the gradient of the flux is maximum. Okay? Then at position 2, when the gradient, at position 2, when the gradient, when the flux is maximum, the rate of change of the magnetic flux is 0. So the induced current or induced voltage will be 0. If the gradient is flat, voltage is 0. At position 3, when we rotate it 180 degrees, then what we found out is actually the magnetic flux is 0 again, but we have a negative gradient. It's decreasing. So the gradient is maximum, then we have a minus voltage because the gradient is decreasing. Okay. Yep. Then at position 4, okay, we have a minimum, we have a turning points. The gradient of turning point is 0. Okay. We have a maximum flux, but the rate of change of flux over time is 0, so we have 0 voltage. Okay. Then it goes back to the original point. If you sketch it, you have a cosine graph. Okay. So yep, that's it. Okay. So if you do, yep. So have a look at it carefully. You'll find it in your textbook or in your notes, page 3.3. Okay. If you have, yep. If you go to your page 3.3, you say it in your notes. So okay, and I don't think I made a mistake, so this should be all right. And yep, just give me a second. Yep, that's it. So okay, one more last thing. The period or the frequency. The period and the frequency. Just ask yourself, what is the time it takes for this whole cycle on the graph? The time is exactly the same as the time we rotate the shaft in one cycle. So the period is basically the time when we rotate the shaft, time of rotation. Okay, that's it. Okay. So the frequency, remember, frequency is how many period in 1 second. Frequency is basically how many, well, the number of rotations per second. So if uh, if I build my own AC alternators, okay, and somehow I'm producing an AC current at 50 Hertz. Okay. This means somehow I'm basically, the rotor in the AC alternators basically rotates 50 times every second. Okay. That's, yep. So, and as a matter of fact, let's just remember this, as a matter of fact, uh, when we talked about Australian power supplies, 230 volts and 50 hertz, it doesn't mean that in our power plant the rotor rotates 50 times per second. It rotates more, much more than that. What they do is they somehow change after they produce the electricity, they change the frequency. But for a simple AC alternator, that's exactly what happens. If you connect a wire to your AC alternator the frequency will be the number of rotations per second that the rotor rotates.